Hey guys, my name is Luke Shannon and I'm a graduate student at Clemson University's International Center for Automotive Research. And today I got a really cool tour to show you of some of the experiments we're doing in one of our engine labs. Let's check it out. Alright guys, this is one of our engine labs. And this is one of our professors, Dr. Lawler.
Hey Luke, thanks for stopping by. Happy to show you our lab and show you what we're working on today.
Alright, great. What do you guys got going on?
All right, so come over here and we'll show you a little bit about this engine. This is a 13-liter, 6-cylinder, heavy-duty truck engine. This is the type of engine that is out of a Class 8 truck, oftentimes called an 18-wheeler, casually, or sometimes called a semi. So these engines are working incredibly hard for civilization and society to pull a lot of goods, transport a lot of things all across the country. We would love to try to improve the efficiency and reduce the emissions of these types of engines. And a long-term goal would be to try to get them running on some sort of renewable fuel. But let's show you a little bit more about what we're working on specifically with this engine. So clearly we've taken the engine completely apart, and we have one of the components over here, which is the piston. So this is the piston out of one of the cylinders of that 6-cylinder engine. You can see we previously ran it. You might be able to see the soot plumes impinged on the surface of this piston. And you can see that we have computer models of the piston as well. And in addition to all of the experiments that we do, we also do modeling and simulation. So we'll tell you a little bit more about that. All right, so this is Mohit Kumar, who's a PhD student who does a lot of our CAD modeling, our computational fluid dynamics modeling. That's modeling where we solve for all of the fluid flows and even combustion processes that go on inside the cylinder of an engine. So Mohit, show us a little bit more of the CAD.
Sure.
So here you can see the CAD of the piston that we were just holding. And Mohit, if you rotate that around, we can see different sides of the piston. You can start to see the wrist pin bore. And you can see all the different dimensions that we have in this CAD model. What we then do is we take this CAD model and we import it into a software that we use that does computational fluid dynamics modeling. And it's called Converge CFD, and here it is. So this is the software where we import all of those geometries and we solve for those fluid flows as the intake air comes in through the intake valves, as the valves open and close and the piston moves up and down in the cylinder. All of that is solved for in here to eventually solve for that combustion process and the thermodynamic cycle that goes on. And we'll show you a video animation of that over here. So here is this video animation of the combustion process in this engine. You can see the fuel sprays come in. There are 8 of them. Is that right? Okay, perfect. There are 8 spray plumes that come in. Let me run that video for you again. And it shows the spray coming in and then burning as it mixes with the air. That's the diesel combustion process. It's a very heterogeneous process, meaning there's a large amount of gradients locally in the cylinder. So some regions may only have air and other regions only have fuel and everything in between, and it burns while it mixes.
I'm seeing that you got a bunch of different colors there. Can you kind of give us an idea of what the color gradients and what the colors represent?
Yeah, great question. So as the fuel comes in, it mixes with the air and it burns. And when it burns, it gets very hot. So those color gradients are actually different temperatures that are going on in the cylinder. And the temperatures in the cylinder go anywhere from 400, 500 Kelvin up to maybe over 2000 Kelvin locally in these spray plumes.
And those are the measurements that you're taking with the piston. Those are basically temperature measurements with thermocouples?
Exactly. So all of the temperatures that you see in this graph are all temperatures of the working fluid, meaning of the gas, the air that's in the cylinder. But what we then do is take those simulations and we take the heat flux that comes out of those simulations and put them as the input conditions to a finite element solver, which basically solves for the heat being imposed on the surface of a metal component. And in this case, this is a top-down view of the piston. And this is how that combustion process causes the piston to locally heat up under each one of those 8 plumes. So what we then do is we wanted to instrument a piston, just as you said, Luke. So we took a piston and we took our simulations and we decided where we wanted to put different sensor locations for temperature sensors. And you can see that in this graph here where we have different locations in the plume or just off the plume. These locations were picked intentionally to try to resolve the gradients of temperature that you can see exist due to those spray plumes. And here's a picture on the right that shows a piston that was instrumented with these different thermocouples, we call them. Those are just temperature sensors at different locations around the piston. We have Kunal Vedpathak, who's a PhD student, and he's going to show us a little bit more about the physical hardware.
So this is our instrumented piston. It is identical to the stock one. It has both subsurface or embedded thermocouples and surface thermocouples. And the cool part about this is it has wireless charging for the thermocouples and a wireless transmitter. So as the piston moves from top dead center to bottom dead center, the system gets charged each time it is at bottom dead center. And we can take a look at the charging hardware inside the sleeve too.
Okay, that's awesome. So basically, you have wireless data being transmitted, and of course, because the piston is moving up and down in the cylinder bore, and it's not fixed like the head, if you had thermocouples in the head, it would be easier just to wire it up hardwired. But because it's in a piston that's moving up and down in the bore, we need to have a way to do it wirelessly.
Exactly. You wouldn't be able to get those wires out of the cylinder if you tried to do it in a wired way, so we need to do it wirelessly. So this is the cylinder liner that these guys removed from this block. And you can see that's just a regular liner. But now Kunal will show you a little bit more about this new instrumented liner that has that inductive power supply in the bottom of it.
If we look inside the cylinder, you can see the charging coil for the wireless charging system. And it is hardwired, and the wire will be done through a hole in the block.
The little square device right there at the bottom. Got it. Okay, and then how do you transmit it through? Is there a port over here? Is that what this is right here? Through the sidewall?
So that's...
Yes. Those are the wireless antennas. We have two on each side, and they will be connected to a DAC box, which will then transmit it to the computer.
So essentially, we can get power from that little square we showed you by looking down the cylinder bore. But to get the actual data signal out, you need to use these antennas. So this is actually what wirelessly receives the data signal. And we had to drill holes into this engine block. It was a little bit scary. So just to show you a little bit more, obviously the head is off and the oil pan is off. If you get down there, you can actually see the crankshaft under the engine. And you can see that 5 out of the 6 cylinders are exactly the way that they would be. And we're only instrumenting this one cylinder, cylinder number 2, with this inductive power supply and these antennas so that we can measure the temperatures at different locations on the piston. And that's why you see 5 out of the 6 pistons are still in the engine. And the other thing we can show you, I guess, is the head. And this particular head has a split head. So this is the lower half of it that has the valves.
All right, yep, I see that. Pretty cool. All the valve springs right there and the valve train.
And one thing that's unique about this particular head are these ports. These are actually ports that are machined in, so that's not in a production engine. This is only in this research engine. They're machined in so that we can put a sensor down through that port to measure the pressure in the cylinder.
And then what do we have over here? This is the other part of that head?
Exactly. So it's a split head where the lower half houses the valves and the upper half houses the camshafts, and that's what you see here. So these guys, as PhD students, took this whole engine apart just so we could get to that piston and that cylinder liner, swap them out, and now they're going to start the process of rebuilding the whole engine so that we can run it and measure that data.
Okay, cool. So how long does a project like this typically last?
Great question. Oftentimes, it can be years. So we've been working on this for probably about 1.5 years, and we're looking forward to taking the data over the next 6 months. So it'll be about a 2-year project. But to do all of the modeling and simulation, to get that initial set of data, and then tear down the engine, put this instrumented piston in, build it back up, and run the engine again, that takes a long time.
All right, awesome. Is there anything else you guys want to share about this engine or this experiment? Or if anybody wants to get more information, where should they go?
Yeah, we're happy to always talk more about our work. If you're looking for more information, there's a lot of great content on this YouTube channel, so please feel free to check out all of those videos. There's also links to various websites related to our department and the different programs we have, as well as the research labs. So please feel free to check all of those out. And then if you still have questions, please feel free to reach out by email. We'd be happy to direct you to the right place or try to answer your question over email or Zoom.
Awesome. All right. Thank you, Dr. Lawler. Appreciate it.
Yeah, thank you, Luke.